Okay, good morning, everyone. Today is the 25th, Monday. So if you look at what we have to do for class today, I'm going to be lecturing on states of matter and phase changes. And then after that lecture, your job is to complete this worksheet. I did include the answers here for you. One little thing, though, is on the original thing that I made copies for you that you have in your Google Drive. This, on the second page of the worksheet, there's a graph here, and I changed it. So this is the new one that you're looking at right now that I'm showing you, but you have a different one. I think this one's just easier to read. The numbers are a little bit more clear. So when you get down to the second part of this and you start reading these questions down here, especially 1 through 6, refer to this graph here. You could even copy and paste it into your document if you like. Okay. All right. So just keep that in mind. And I'll try to remind you guys when I'm done lecturing here. But last time we talked about the states of matter and how they really depend on two different things. The intermolecular forces, or the forces between particles in a system. So inter meaning between, molecules, molecular meaning molecules, and forces meaning the push or pull. So the push or pull between molecules in a substance. So how strongly are they attracted to one another, basically. And then the other thing that states of matter depend on is the kinetic molecular theory. So how fast they're moving. So how much motion they have. Okay, so two factors: how fast are they moving, and how strongly are they held together. Okay, we talked a little bit about the difference between intermolecular forces and intramolecular bonds. So intramolecular means within molecules, so the bonds within molecules. And those are things like ionic, covalent, metallic bonds. Those are the things we're going to get into next unit, not so much this unit. The other one is the intermolecular forces. Those are again, between the intermolecular forces between. We're not actually going to ever talk about what the different types are, dipole, dipole. We're not really going to talk about any of those things. But just know that these are the things that determine physical properties. Okay? So intermolecular forces are the ones that determine physical properties, and one of those physical properties is states of matter. The states of matter are what we're going to talk about today. Okay? We talked a little bit about kinetic molecular theory. Last time, again, all substances are composed of particles. They're always in motion except at absolute zero, which is 0 Kelvin. The collisions are perfectly elastic, meaning they don't lose or gain energy overall. They may transfer energy from one to another, but they don't lose it overall. And then finally, the average kinetic energy is equal to is proportional to the Kelvin temperature of the system. So we talked about all those things last time. Okay. And then we also looked at the temperature scales, the 3 temperature scales that we need to be familiar with. The first one, Fahrenheit, is most people are familiar with that one. That's the one we kind of use in everyday life, right? That's the one we tell temperature with pretty much always in the United States, at least. And then there's Celsius. Celsius is the one that most of the time you're gonna use in Europe, or in science we use Celsius a lot. And then finally, Kelvin. Kelvin is a new one you may not have heard of, but Kelvin is important because we set Kelvin absolute zero at 0 Kelvin. Okay, so at 0 Kelvin, there is no molecular motion. We can't get any colder than that. Remember that temperature is all in relation to the motion of the particles. We also talked about how the 1 degree Fahrenheit is not equal to 1 Celsius. However, 1 Celsius and 1 Kelvin are the same. So Celsius and Kelvin are the same increments of change. We looked at how to convert those temperatures, and you did some practice with that. Okay, now what we're going to talk about today is the phases of matter and how their intermolecular forces are, what kind of intermolecular forces they have, and what the motion of their particles is like. So in gases, there are no intermolecular forces. At least in ideal gases, we consider there are no IMFs. So IMFs is just short for intermolecular forces. And we consider gases to have no IMFs. Liquids, there's enough kinetic energy to break the IMFs temporarily, so they can slide past one another. There are intermolecular forces, but again, they're broken and then made constantly over and over and over again. Okay. Solids, the IMF bonds in solids hold the atoms and molecules in place. So the particles just vibrate in place. Okay, so now we're going to look at all those a little more closely. First, solids. We're going to kind of go backwards here. So solids have the least kinetic energy, the most attraction to one another. They are vibrating. They are vibrating in place, though. They're not totally motionless. They just move in place. But they don't have enough energy to overcome those intermolecular forces, so they're kind of stuck together. Okay. These little lines here indicate that they're vibrating. They're vibrating in place. Usually you'll see more like arrows. If you're ever asked to draw a solid and the molecular motion, you should draw tiny little arrows, just like this. So this shows like the solid just vibrating in place, very, very little bit. Okay, and the longer the arrows, the more they're vibrating, the higher energy they have. Okay, and we also have to remember that solids, we always know that solids have a definite shape and definite volume. Right? We cannot compress a solid. There may be space in between solids, but overall you cannot compress a solid. All right? They have a definite shape, definite volume. They're non-compressible. You can't really change their shape. It takes energy to compress them, and it takes energy to change their shape. Right? If you wanted to change the shape of a metal, you have to put energy in it to bend it and move it. You know, it's hard to change the shape of a metal. Just think of it that way. Liquids have medium kinetic energy, so somewhere in the middle. So you'll see these kind of the medium-sized arrows. Okay. Molecules have enough energy so they can kind of slide past one another. They temporarily overcome the intermolecular forces and then form new intermolecular forces with other molecules or atoms around them. Okay, so this is kind of showing these ones sliding around, right? And these ones are just kind of moving in linear motion, but that's fine too. Volumes have an indefinite shape, so they can kind of they fit into whatever container you put them in, but they do have a definite volume. Liquids are non-compressible. You cannot compress liquids. That's what hydraulics. That's how hydraulics work. Hydraulics work with your trying to compress the liquid, but it doesn't. So it transfers that energy to something else. Okay. Gases, particles have very, very high kinetic energy. We consider that they have no intermolecular forces. Now, that's not entirely true. There are slight intermolecular forces and attractions between gas molecules. But for the most part, we just think, okay, gases do not interact with one another. They don't have intermolecular forces. And that would be an ideal world, but that's not exactly true. There you have an indefinite shape and indefinite volume. You can compress gases, you can expand gases, you can put them in all sorts of different containers. Doesn't matter. Okay, and you'll see longer and longer arrows as we go from solid to liquid to gas. So gases should have the longest arrows, indicating the highest amount of kinetic energy. Okay, the next thing, we got to talk about all the different the different names of the changes and phases of matter. So you do need to memorize these and know what they are. And we're going to talk more about what happens as these phase changes are occurring. So if we're going from solid to liquid, that's called melting. If we go backwards from freezing to solid, it's called, liquid to solid, it's called freezing. And then if we go from liquid to gas, we call that evaporation or vaporization. Really, vaporization is more accurate. Evaporation is occurring below the boiling point. Then gas to liquid, we call that condensation. Okay. Then we can also go from solid directly to gas or gas directly to solid. These two terms are terms that people don't often remember or know. If you go right from gas to solid, we call that deposition or deposit. It's depositing a gas to a solid. If we go from solid to gas, sublimation. You might see that with like dry ice. Okay, dry ice, carbon dioxide, solid carbon dioxide turns to gas immediately at room temperature. So you may have seen that before. Now, these changes in phases of state of matter are due to energy being either released or absorbed. When energy is released, we call that exothermic. And when energy is absorbed, we call it endothermic. Okay. Now, I think energy enters. Endo enters. So energy enters the system. Okay. Enters whatever we're talking about. The system is just whatever we're talking about. And then exothermic energy exits the system. And again, the system is whatever we're talking about, whatever we're looking at, whatever we define as the system. Okay. Now, don't think of it as a change in temperature, because in physical changes, when we talk about phases of changes of matter, okay, endothermic, you'll always get the temperature decreasing. Okay, the temperature will, I'm sorry, the temperature will increase. The temperature will increase. Now, that works for a physical change, for a phase change. If we want to turn something from solid to liquid, we have to add heat to it. We put heat in, it enters, and the temperature goes up. Okay. Now, if we actually have a chemical reaction, and the chemical reaction actually starts to get colder to the touch, that's actually an endothermic reaction. So it's actually getting colder. So that's why I don't like if and when you get to eventually take chemistry, you'll see that it's different in a physical change and chemical change. They're opposites. So I don't like to think of it as is the temperature changing? What's happening to the temperature? I think about it, where is the energy going? Is it going into the system or out? Okay, same thing with exothermic. Exothermic in phase changes, we're getting colder because the heat is leaving the system. So it's getting colder and colder and colder. However, in a chemical reaction, usually a chemical reaction will be giving off heat. It'll feel hotter than the surrounding system. It'll be starting to give off, so that the temperature actually rises. Okay, so don't think about it as temperature change. Think about it as, is the heat going into the system or out of the system? Into endo, exiting exo. Okay, it's kind of tricky, but I think if you think of it that way, it makes it a lot more clear. Okay, next thing we're talking about here are these phase change diagrams. So there's two types of these things. There's phase change diagram and a phase diagram. We're going to talk about both of these things. They're very different, and yet they have some differences and some similarities. Okay, but sometimes they call them both phase diagrams, and sometimes they call them both phase change diagrams. I like to just keep it consistent, call these phase change and these phase diagrams. Okay, these phase change diagrams show the change in phase of matter over time as we add heat energy to it. Okay, so what's happening here is we have on the y-axis we have temperature, okay, or overall kinetic energy, right, or average kinetic energy, and on the x-axis, I'm going to move this up a little bit, so this keeps bothering me. So on the and then on the x-axis we have heat energy. So heat energy being added. So it's just like heat energy being added over a given amount of time. Okay, no specific amount of time, just kind of over time. All right, and it's being added. The heat energy is being added steadily to the system here. Okay, and every type of matter has a different phase change diagram. Because really what these flat areas in the phase change diagram, what they represent, these flat areas, this one and this one, is our phase changes. That's basically what the diagram is showing, the phase changes. So here we start as a solid. It's very low, not a lot of heat energy, low temperature. And then we're going to add heat energy, and as we add heat energy, we get a steady rise in temperature until we get to this point here. Now this point is the melting point. And then as we add heat energy, we don't see a change in temperature. What's actually happening is all of this heat energy that's being added is going into breaking those intermolecular forces. So it takes energy to break those intermolecular forces. That energy, that heat energy, instead of increasing the temperature, instead of increasing the kinetic energy, it's instead changing the potential energy. So potential energy is the energy stored in the intermolecular bonds. So it's increasing, melting, all the way until we get to all of it's going to be a liquid at this point right here. At that point, it's all going to be a liquid. Okay, and then the heat energy will again increase the temperature at a steady rate again. Okay. Now, if you didn't notice already, the melting and freezing actually happen and occur at the same exact temperature. This is something that really blows a lot of people's minds, makes a lot of people, they don't understand this. They get this confused a lot. The freezing point of water at 1 atm or at normal, at sea level, is 0 degrees Celsius. You know what the melting point of water at 1 atm is? 0 degrees Celsius. The melting and freezing points are the same temperature. Okay? It all depends on which direction you're going. Are you adding energy? If you're adding energy, then you're going to have it be turning into a liquid. If you're removing energy, it's going to be turning into a solid. Okay, so you can have liquid water and ice both at 0 Celsius. Okay, we have what we call an equilibrium here. Okay, some of it's freezing, some of it's melting. Okay, some of it's liquid, some of it's solid. Okay. Now, if we keep going, eventually we'll get to the next point in the equilibrium here, vaporization and condensation. So for water, it's 100 degrees Celsius. It vaporizes, turns into a gas. Okay, same thing. It condenses at 100 degrees Celsius as well. Okay, so both steam and water can be at 100 Celsius. Okay, boiling water is at 100 Celsius. That vapor coming off is also at 100 Celsius. It all depends on what direction you're going. Okay, so that's a phase change diagram, solid to freezing or melting, and then to liquid, then condensation, vaporization, then gas. All depends on which way you're going. You can go backwards too. You can release the heat energy and go backwards. Okay, the one to the right here is just a more accurate description, just showing how much energy is needed to change these temperatures. So initially it's like 50 calories per gram. Or maybe not 50, but it's probably more like 48 calories per gram. And then to go from -20 to 0. And then to melt a gram of water takes that much energy. So 50 calories or whatever that is, 50 calories. And then this much energy to heat the water up to 100. And then this much, a lot of energy to turn water to steam. It's a lot of energy to turn water to steam. Okay, we're going to talk more about these graphs when we get into thermodynamics, or I'm not sure actually if we'll get to thermodynamics in here, because sometimes we just cover it in chemistry. We might not get to it in this 9th grade class, but you'll see this again in chemistry. And the last thing we'll talk about here is the phase change diagram. So a phase change diagram shows different pressures and temperatures. Pressure on the y-axis, temperature on the x. And then given a certain pressure and temperature, you can figure out what state of matter this substance is in. So you say this pressure and this temperature, and you find where they meet, and you'll know it's a liquid. This pressure and this temperature, you'll find where they meet. It's a solid. This pressure and this temperature, it's a gas. Okay? The lines separate the different phases of matter. If you go from solid to liquid, that's melting. Liquid to solid, it's freezing. All these other ones as well. Vaporization, condensation, sublimation, deposition. Okay. There's a couple of points on the graph that we have to point out here. This point right here, you see all 3 phases of matter are intersecting here. You have solid, liquid, and gas all intersecting right here. We call that the triple point. Okay. The triple point is where all 3 phases of matter are in equilibrium. So slight change in temperature or pressure can cause them to go from liquid to solid or liquid to gas, gas to liquid. They can go between all 3 of these phases just by very, very slight changes in pressure or temperature. Okay, and then the critical point is the temperature at which the liquid and solid lines no longer mean anything. Okay, and really after this temperature, you can no longer have a liquid. You have something else called a supercritical liquid. Okay, but we're just going to consider that it can no longer be a liquid. After this temperature, it can no longer be a liquid. Doesn't matter how much pressure you put it under, it's no longer a liquid. Now this line here between liquid and solid is very, very important. It tells us whether the solid is either denser than the liquid or less dense than the liquid. So will it float in the liquid? This line here has a positive slope. Okay, it's slightly to the right. So it's going slightly to the right. We call that a positive slope. And that means that the solid is denser than the liquid and it will sink in the liquid. Okay? If this slope was negative, meaning it goes backwards, that means the solid is less dense than the liquid, just like water. Okay? Liquid water is denser than ice. It's a weird kind of thing there. It's it's a very strange property of water. Okay? That solid water is actually less dense than liquid water. And you'll see in these, I'm going to show this graph again here. We have these two graphs. On the left this one is carbon dioxide. You'll see that this is a positive slope, meaning that the solid is denser than the liquid, which is makes sense, right? Solid should be denser than the liquid, more compact. This one though is for water. You'll see water has a negative slope. Therefore, the liquid is actually less dense. Sorry, the liquid is more dense than the solid. The solid is less dense. The solid floats in water. Solid floats. So solid water, ice, floats in water. It's a really important property of water that has allowed really organisms to survive. Okay, it's a very, very important property of water. Okay, and that's it. I'm done. Hopefully that helped, and good luck on the worksheet.